Welcome to Lecture B12. In the last lecture, we talked about discrete random variables, and in this one, we'll talk about continuous random variables. And just as we did before, we'll examine this topic by looking at examples. So let's go ahead and jump right in and talk about problem 24.5.2. We might recall that when we started our last lecture on discrete random variables, our first problem was 24.5.1. 24.5.2, the problem we're about to do, is a very similar kind of problem, but for continuous random variables. And so this problem says graph the density function little f of x is equal to kx squared, and that's for 0 less than or equal to x less than or equal to 5. And again, as reminiscent of the first problem, it says k suitable. And the distribution function. So right away, even from the wording of this problem, we see one small difference between discrete random variables and continuous random variables, and that is that the function little f of x here has a different name. Remember that when we talk about discrete random variables, little f is called the probability function, and for continuous random variables is called the density function. And the difference is as follows. Remember that for a discrete random variable, f of a, let's say f of a, so for discrete random variable, x, little f of a is equal to the probability that x is equal to a. What does f signify for a continuous random variable? Now, this might be a little puzzling to you. You might say, well, why doesn't little f mean the probability? Why doesn't f of a equals the probability that x equals a for a continuous random variable? And I'll answer that question in the following way. Suppose that we have a line here from 0 to 1, and we asked, let's say that we are throwing a dart somewhere on this line, and it can land anywhere on the line. And let's suppose that we want to know the probability that the dart hits 0.5. What would that probability be? Well, remember, when we say that the dart hits 0.5, we mean actually that it hits 0.5000000 and on forever with zeros. We don't mean 0.500000001. That's a different number. We mean 0.5 and then zeros forever after that. Well, the probability that we're going to hit exactly that number is 0. In fact, the probability that we will hit any one of the uncountably infinite number of real numbers between 0 and 1, the probability for any single one of them is going to be 0. So when we're talking about continuous random variables, where the random variable can assume a value anywhere in some range like this, then it's no longer helpful to think about the probability that the random variable assumes any particular value. Instead, what we do is talk about the probability that the random variable will be in some range. And so for a continuous random variable, what we have is the following. The probability that the random variable will have a value in some range, in a range between A and B, where we're understanding here that A is less than B, is equal to the integral from A to B of f of lambda d lambda. Now, lambda there, don't get confused by that. Lambda is just a variable of integration, a dummy variable of integration. So you could call it lambda, you could call it t, you could call it little x, whatever you wished, because it's going to integrate out anyway. But that is what the little f, or in other words, the density function, that's what it means for a continuous random variable, is that if we want to know the probability that the random variable has a value between A and B, then it's the integral from A to B of that density function. And one more comment here. Notice that, again, since x is a random variable, it's not really very important whether we have less than or equal to here or strictly less than, because the probability that x is exactly equal to A or that x is exactly equal to B is 0. So we could have, we could just as well here say probability that A is less than x is less than B. That would be fine. We could even say probability that A less than or equal to x less than B, or probability that A is less than x is less than or equal to B. For a continuous random variable, all of these will be equal to the same value. Now, that's not true for a discrete random variable. Certainly, it's important for you to understand that for a discrete random variable, that would not be true. And that's why we were careful when we were finding the cumulative distribution functions for discrete random variables in our previous lecture. We were very careful to know whether we needed to use less than or equal to. But here, it doesn't matter. Now, another note along these lines before we go ahead and jump into this problem is the following. For both discrete and continuous random variables, we have that the cumulative distribution function, or also called the distribution function, f of little x is equal to the probability that the random variable x is less than or equal to little x. That's true for both discrete and continuous random variables. So, for a discrete random variable, this is a little bit of a review here. F of x is equal to the sum over all y less than or equal to x of f of y. If we look at all the values that the random variable, all values y that the random variable can assume all those values that are less than or equal to little x, and we add up the corresponding probabilities, then that will give us the probability that the random variable has a value less, the total probability that the random variable has a value less than or equal to little x, and that, of course, is capital F of x. Well, for a continuous random variable, remember now that we saw above that the meaning for a continuous random variable, the meaning of the density function is that the probability that the random variable is between a and b, well, that's simply the integral from a to b of the density function. Well, let's think about this now. For a continuous random variable, we've already said that for both continuous and discrete random variables, that f of x is the probability that the random variable is less than or equal to x. So let's just repeat that. That's the probability that x is less than or equal to x. Well, note that another way of writing that is to say the following. Negative infinity is less than x is less than or equal to little x, because certainly the random variable can't have a value less than negative infinity. So we can use that as the left limit. And then, of course, we note once we have it like that, that matches exactly this one of these four forms here that we said above were all equivalent, and all of those were equal to the integral from a to b of f of lambda d lambda. But in this case, a is negative infinity and b is little x. You see here, compare this expression with this one, and you see, again, as we said, a is negative infinity and b is little x. And so in this integral, we replace a by negative infinity and b by x. So we have integral negative infinity to x of little f of lambda d lambda. And that is the relationship between the density function and the cumulative distribution function for a continuous random variable. And just a couple of other quick notes, and then we jump into this problem. Note that as with discrete random variables, f of negative infinity is equal to 0. That was true for discrete random variables, and you can see if we plug in negative infinity for x, then we have the integral from negative infinity to negative infinity, and so we get 0 there as well. We'll say, note also that f maybe I don't want to say note here. I'll write it like this. We also have probability that negative infinity is less than x is less than infinity is equal to integral from negative infinity to infinity of little f of lambda d lambda. And of course, that's the probability that x has some value, which of course is 1. And this is the same thing as, of course, capital F of positive infinity. So capital F or the cumulative distribution function of positive infinity is equal to 1 for a continuous random variable, just as it was for a discrete random variable. And by the way, this equation right here is what will allow us to find k in this problem. You remember that for the discrete, when we did problem 1 for the discrete random variable, we said that if we added up all of the probabilities, they had to equal 1, and that's what allowed us, that key observation was what allowed us to find k for problem 1. And now for problem 2, it's really the same kind of thing. We're going to integrate all the probability to get the total probability of 1, and this will allow us to find k. So I believe we're ready now. We've done enough background review to go ahead and finish this problem. So once again, let's review what the problem says, and then we'll jump right into it. So it says, graph the density function f of x is equal to kx squared, where x is between 0 and 5, and k is chosen suitably. And we also want to graph the distribution function. So the first thing we need to do in order, if we want to graph little f of x, before we can graph it, we need to find what k is. But now this last observation is what will allow us to do that, because we have that the integral from negative infinity to infinity of f of lambda d lambda is equal to 1. And recall that in this case, f of we can say f of x or f of lambda, it doesn't matter what we call it. F of lambda is equal to k lambda squared for 0 less than or equal to lambda less than or equal to 5. And although they didn't explicitly state it, what that means is that it's equal to 0 elsewhere. So this integral on the left-hand side here could be written as, you know, when we integrate from negative infinity to 0, we clearly get 0 because f is equal to 0 everywhere there. Actually, let me just make sure this is clear. So we can break this up into an integral from negative infinity to 0 plus integral from 0 to 5 plus an integral from 5 to infinity. Okay, that's just a restatement of this equation right here. But our definition for f of lambda says that it's equal to 0 whenever lambda is outside the range 0 to 5. So this first integral becomes the integral from negative infinity to 0 of 0 d lambda. The second integral becomes integral from 0 to 5 of k lambda squared d lambda. And the third integral becomes integral from 5 to infinity of 0 d lambda. And that's equal to 1. And of course, when we integrate 0, we get 0. So the first and the third integrals go away. And for the second integral, the k is a constant. So we get k times the integral from 0 to 5 of lambda squared d lambda is equal to 1. And so this says k times lambda cubed over 3 evaluated from 0 to 5 is equal to 1. And therefore k times 125 over 3 minus 0 over 3 is equal to 1. Or k times 125 over 3 is 1, and therefore k is 3 over 125. So that would be the value of k for this problem. And now that we know k, we can plot. We were asked to plot little f of x So here's x, and here is f of x. And remember, we only have to consider from the range from 0 to 5, because it's equal to 0 everywhere else. So we can say 0 and 5. And this is equal to kx squared, which is equal to 3x squared over 125. And so let's just think about this for a moment. The largest value that f of x will have is when x is equal to 5, and when it's equal to 5, it'll have a value of 75 over 125. So let's see real quick. Let's take a quick break and get a calculator here. Well, we don't need, I guess we don't need a calculator for that first one. 75 over 125 is the same thing as 3/5, so we'll have 0.6. So let's maybe do the vertical scale like this: 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. And so at 5 we have 0.6, and we can fill in the others. Of course, this graph won't be exact, but it'll give you a rough idea. At 4, we have 0.384, so roughly here. And for 3, we have 0.216, so about here. And for 2, we have about 1/10. And then for 1, we have 3 over 125, which is about a little more than 0.02, so very small. And now our graph will look like that. And this graph has something in common with the graph of a little f of x in problem 1, and that is that this is a non-decreasing function of x. But as we noted in problem 1, that does not have to be the case for little f. This little f here for continuous random variable, it could have been a decreasing function, or it could have been oscillatory. Now it cannot be negative, but it does not have to be non-decreasing as this is. Now, capital F of x, it's important to know, capital F of x is non-decreasing for both discrete random variables and continuous random variables, but little f of x need not be non-decreasing. In problems 1 and 2, in both of those examples, little f of x is non-decreasing, but it doesn't have to be. So this is the graph for little f of x, and now to find capital F of x, well, remember that's the integral from negative infinity to little x of little f of lambda d lambda. And if that's going to be equal to 0 if little x is less than 0, because remember that if in the range from negative infinity to 0, little f is equal to 0. So if this little x here, if it's some number less than 0, then we would be integrating just 0, and we would get 0. But if little x, Actually, we'll consider 3 possibilities here, so let me change this bracket. If okay, so as you can see from the way that I've broken this up, it's important when you're trying to evaluate this integral, it's important to note where x is. If x is over here to the left, then remember little f, this, although we haven't shown it on the graph here, little f is equal to 0 everywhere over here to the left. And it's also equal to 0 everywhere to the right of 5. Again, we haven't shown that either, but just keep that in mind. So when we're integrating little f here to get big F, if little x is anywhere to the left of 0, then we're just integrating 0 and we get 0. On the other hand, let's drop down now to the third line. If little x is somewhere over here to the right of 5, then we're integrating from negative infinity, and we're going to get this whole area here. And then we'll also extend over into this region where little f is back equal to 0 again. Now we don't have to include that, because when we integrate 0 we don't get anything, but we do need to include this whole region where little f is non-zero. And so that's why for the third line, when x is greater than or equal to 5, this just capital F just becomes integral from 0 to 5 of 3 lambda squared over 125 d lambda. But if little x is somewhere in between 0 and 5, then we want to integrate simply from 0 to x. We only want to get that part that is to the left, that is less than or equal to x. And so this would be our expression for capital F of x. And now if we evaluate this, okay, for this part, when we integrate lambda squared, we're going to get lambda cubed over 3. So we get lambda cubed over 125, because the 3 will cancel this 3. So we get lambda cubed over 125 from 0 to x. And for the bottom one, when we integrate, we'll get lambda cubed over 125 as well. But the limits will be 0 and 5. And now to evaluate that. When we evaluate that, this is what we obtain. And notice once again that capital F of negative infinity, that would fall in this first case where we're looking at if x is less than 0, and capital F of negative infinity is indeed 0. And capital F of positive infinity, that would fall in the third category, and that is 1. And finally, also note that capital F is a non-decreasing function of x. In other words, as x increases, capital F is always going to either remain constant or get larger. It will never get smaller. We can see that. You could plot this function, and this function is so easy to plot. Let me just real quickly note. Okay, so we'd have 0, 1, 2, 3, 4, and 5. And if we call this 1, and this is 0, then everywhere to the left, capital F of x is equal to 0, and everywhere to the right of 1, or to the right of 5, is equal to 1, and in between here, it varies as x cubed, and, well, I guess we could do this real quickly. So, 4 cubed over 125 is going to be very close to 1/2. Let's see. So we have 0.512, so let's see. I guess this would be 0.2, 0.4, 0.6, 0.8, and so this would be roughly there. And this would be about here. And this would be quite the pen stopped working for a moment, so let me. Oops, sorry. Okay, so let's see if this is going to work right. And with 1, it's going to be very hard to see this. So anyway, this graph would look something like that. So you see that indeed this is that capital F of x is a non-decreasing function of x, and it goes to 0 as x goes to negative infinity, and it goes to 1 as x goes to positive infinity. So that's how you would complete problem 24.5.2. And so now let's look at another problem with continuous random variable. For the next problem, let's consider 24.5.12. And this problem says, let x be the ratio of sales to profits of some company. Assume that x has the distribution function f of x equals 0 if x is less than 2, f of x equals x squared minus 4 over 5, if 2 is less than or equal to x is less than 3, and f of x is equal to 1 if x is greater than or equal to 3. Find and sketch the density. Let's just, I'm not going to worry about the sketch. Let's just say find the density, and also what is the probability that x is between 2.5 and 5. So let's maybe start with the second question. Well, actually, notice that to answer this part that asks you for the probability that x is between 2.5 and 5, that's simply the integral from 2.5 to 5 of little f of lambda d lambda. But we don't know little f of lambda. And of course, that's the first part of the question. It says find the density, which is the little f function. So we simply need to find little f and then integrate it to get the answer for the probability. Now recall that f of x is equal to the integral from negative infinity to x of little f of lambda d lambda. But this implies that little f of x is equal to the derivative of capital F with respect to x. And therefore, since in this case, well, let's maybe write it down like this. So we know, summarizing what is given in the statement of the problem, we know that if x is less than 2, then capital F of x is equal to 0. And if 2 is less than or equal to x is less than 3, capital F of x is equal to x squared minus 4 over 5. And finally, if x is greater than or equal to 3, f of x is equal to 1. And so if we want the density function, well, we just take the derivative And of course the derivative of 0 is 0. And that's in the region x is less than 2. And the derivative of x squared minus 4 over 5 is 2x over 5. And that's in the region 2 is less than or equal to x is less than 3. And the derivative of 1 is 0. And that's in the region x is greater than or equal to 3. So here is the density function for this random variable. And now to answer the second part, we could do this in a couple of ways. As I mentioned before, one way well, let me remind you, the second part of the question is, what is the probability that x is between 2.5 and 5? One way of doing this would be to take this density function that we have just derived and to integrate it from negative infinity, integrate it from 2.5 to 5. But an even easier way to do it is the following. So the probability that x is between 2.5 and 5, and as we noted before, since x is a continuous random variable, it really is not critical here whether we have, the statement between 2.5 and 5, does that mean it includes the endpoints or not? Do we want to include the possibility of x being equal to 2.5 and 5, or do we want to exclude that or include one and not include the other? Well, it doesn't matter because this is a continuous random variable, and the probability that x is identically equal to either one of those values is 0. So it doesn't really matter here if we put the less than or equal to in either of these cases, but P, the probability that 2.5 is less than x is less than 5, that's the probability that we want. And actually, I guess, okay, let me maybe say it like this. If we want to be real picky, then maybe what I will say, okay, is this. As we have already stated before, let me just make this perfectly clear. So this is the same as 2.5 less than or equal to x less than 5, which is the same as the probability that 2.5 is less than x is less than or equal to 5, which is equal to the probability that 2.5 is less than or equal to x less than or equal to 5. And once again, I want to stress this is only true because x is a continuous random variable, and with a discrete random variable, it can make a big difference whether or not we include the endpoints. But with a continuous random variable, it does not. Now, in this case, I want to help you see that there is an easy way to do this. Note the following. Okay, we have this capital F function. Now we know that capital F of 5 is the probability that x is less than or equal to 5. And capital F of 2.5 is the probability that x is less than or equal to 2.5. And therefore, if we take the difference between these two probabilities, we have the probability that 2.5 is less than x is less than or equal to 5. But note that that matches exactly one of the probabilities up here that we listed, And therefore, so this is, let me maybe put it like this. All of these are equal to probability that x is between 2.5 and 5, which of course is what we're asked here in the question. What is the probability that x is between 2.5 and 5? That's what we want to find out. And as we've already explained, that could be written in any one of these four ways. But one of those ways is precisely, it exactly matches the definition of capital F of 5 minus capital F of 2.5. And that's particularly convenient because we already have capital F given to us right here. So if you don't want to integrate little f from 2.5 to 5, then an alternative way to solve this problem is simply to calculate capital F of 5 minus capital F of 2.5. Now, I encourage you, just as extra practice, we're going to go ahead and finish this problem, go ahead and evaluate this, but I encourage you to do it the other way as well. In other words, integrate little f from 2.5 to 5 and make sure you get the same answer. But what we will have here then is the probability that x is between 2.5 and 5 then is equal, as we've just argued, is equal to f of capital F of 5 minus capital F of 2.5. And now we look above, capital F of 5, as we can see up here, since 5 is greater than 3, that's equal to 1. And capital F of 2.5, well, 2.5 falls in the range here between 2 and 3, and so we get 2.5 squared minus 4 over 5. 2.5 squared minus 4 over 5. And that gives us 5/5 minus 2.5 squared will be 6.25, and 6.25 minus 4 will be 2.25. And so we get 2.75 over 5, or 0. I believe that's 525. Let me check this calculation. Oops, that's wrong. 0.55. So this is the probability that the random variable has a value between 2.5 and 5, and then this here is the density that was requested earlier in the function. And once again, I strongly encourage you to integrate this from 2.5 to 5. Integrate this function and make sure you come up with this same answer. So that concludes the in-lecture problems for lecture B12. And now let's look at some related problems. So the problems for this lecture will be as follows. Both of the problems here are very closely related to problem 24.5.9 in your textbook, and it says the following: let x, which is measured in millimeters, be the thickness of washers. Assume that x has the density f of x equals kx if 0.9 is less than x is less than 1.1 and 0 otherwise. And so question B 12-1 asks what is k, and the choices are A 10, B 5, C 2.5, and D 0.2. And the second question, B 12-2, is what is the probability that a washer will have a thickness between 0.95 millimeters and 1.05 millimeters? And the answers here are A 0.75, and all of these are in, these are probabilities. So A is 0.75, B is 0.5, C is 0.25, and D is 1. And then, as usual, there will be other problems in class. So that concludes Lecture 12, and good luck.